Welcome to Notes on Chapter 11 of Fundamentals of Physics, 8th edition. In this chapter, we'll be looking at and discussing rolling, first without slipping and then with slipping, torque on a hill, and then torque that causes a change in angular momentum after we've talked about angular momentum with the definition and the conservation of angular momentum. So these are the three main topics, and they're all interrelated. So we will have to be having some overlap here, regardless of how I've separated them out with these topics and the subtopics. Let's consider rolling without slipping. Rolling without slipping, what we're going to be doing is we're going to be taking translating motion in which an object slides, let's say to the right, where every single particle in that object, bottom, middle, top, front, back, this diagonal corner, well, it's a circle. Every single piece has the same velocity. So we would call this velocity, that velocity. They all have exactly the same velocity. And we will combining that with rotating. Last chapter we looked at pure rotation. Pure rotation has the object as a whole does not go anywhere. The velocity of the center of mass is 0. And what that means is that the top would move to the right with speed v, and the bottom would move to the left with speed minus v from our perspective, because it's moving to the left, and to indicate that it's moving to the left, we have to throw a minus sign at it. And when we combine these two guys, we get rolling without slipping. What makes it without slipping? Well, this bottom point here, the point of contact between the object of interest and the ground is 0. Instead of having the center be 0 and it just spins in place like a CD or a record, now we're going to have the bottommost point has 0 and the object as a whole moves to the right, because the object as a whole will be translating in addition to rotating. So when we add these two guys together, the bottom with plus v and minus v goes to 0. The center with v and spinning, the center of mass of the object will be moving to the right with speed v. And we typically call that VCM for center of mass. Now the top, this is what's interesting. The top will be moving to the right with speed 2v. So what we get now is a difference in speed, linear speed, depending on where you're looking for the object. And I can illustrate this with a wheel and some meter sticks. So let's consider this bike wheel. And I have some meter sticks here. So let's put this 1 meter stick here at the front there, so that the bottom of that meter stick there is at 0. So the center of mass of our meter stick, and you can't quite tell, I'll line this up with the looking straight down on the axle. So I've got the axle here, I'm looking straight down, and the center of the wheel is starting at the 0 of the meter stick. And I'm going to put this other meter stick on top of the wheel. And this other meter stick, notice how this starts at 0 also, but it's extending to the left. Now watch how far this point on the top of the wheel goes compared to where the center of mass ends up on this meter stick. So how far does the top go relative to how far the middle goes? And if we roll this and we get nothing to slide, now let's take a look here. The center has gone through half a meter. The center has, there we go. The center has gone through half a meter. It's gone from one end of the meter stick to the middle of the meter stick. So that's how far the wheel as a whole has gone. But how about how far has the top gone? Well, the top has gone as far as this end of the meter stick has moved. And this end of the meter stick has moved from all the way down here at 0 all the way across, and it's now lined up with the right side of the meter stick that's on the table. So this point, which has been attached to the top of the wheel, has moved from one end of the meter stick all the way across to the other end of the meter stick. It has moved twice as far. And if I were to continue this so that the wheel moves all the way through the full meter, now the wheel is at the other end of the meter stick, and now this meter, so the center of the wheel is now at the other end of the meter stick. It has moved through one full meter. But how far has this meter stick that's on the top gone? Well, the meter stick that is on the top has gone through this meter. It's gone all the way through that meter, and then it's gone through all the next meter. That's why the opposite end of this meter stick is now sitting on there on top of the wheel. I started with it set up like this, so that this meter stick is off to the side, on the left side of your left side of the meter stick. And then when I roll through here, manage not to have it fall down, it's now pointing off the right side of this meter stick. So it's gone from the left side of the meter stick to the right side of the meter stick, even as the wheel as a whole, as measured by the center of the wheel as a whole has only gone through this 1 meter. Some of you might need to go back and replay this so that you can see how this meter stick has gone through a much farther distance than the center of the wheel has gone through. And that's supposed to illustrate the fact that the top of the wheel is moving twice as fast as the center of the wheel. Meanwhile, whatever point is happening to touch the table right now, it's not moving at all. That point momentarily stops, just for an instant, so that it's not slipping. Because what we're doing here is we are taking the situation, and if I were to set this up so that this thing slid, if I just slide it from one end to the other end, and I don't let it spin at all, you can notice that this top of this meter stick on the top moves along with the center, and this end of the meter stick goes from that end of the meter stick to this end of the meter stick just like the center does. It's gone through 1 meter. So if I start here and I have the thing translate, the whole thing slides, you can see that the bottom and the middle and the top are all moving together with the same velocity, with no difference between them. But if I hold this up here and I spin it, the middle is not going to go anywhere. The top is getting, if I put my finger on it, it gets pushed to your right. Meanwhile, on the bottom, it's going to the left. So if I attach my finger momentarily there, it's going to be moving to the left. But when I put this down and I combine them, I get the situation where the bottom momentarily stops when it comes into contact with the ground. The middle moves with speed, we'll call that v. And then the top is now moving with speed 2v. And we can represent that by the fact that they're moving at the same time. This moves that way at the same time that this guy moves that way. But this point will be moving twice as far in the same amount of time. If you move twice as far in the same amount of time, and there I've gone to the middle of the meter stick again. If you move twice as far in the middle in the same amount of time, you've gone twice as fast. Visualizing this is difficult because it's inherently tied to motion. Can't really pause it to see the effect. We have our previous divisions of motion that we've talked about, which has always been x and y. We've always split apart the x and the y. We've always split apart the x and the y motion. So we've represented this with our xy chart in Wofestad. And it was time that tied together the x and the y. And then when we went to statics and dynamics, we changed our representation of x and y from an xy chart to a free body diagram. And we had our equations for x, and we had our equations for y. And then the thing that tied them together was the coefficient of friction, where we had in the x direction friction, in the y direction the normal force, but then the thing that tied them together was mu. Our new division of motion is no longer going to be x and y. Our new division of motion is going to be translating versus rotating. And we already introduced this in a previous chapter when we looked at rotation and just rotational motion. So we would have the linear version, and we would have the angular version, and now they're going to be tied together by the arc of a circle. So the radius, if you go a radius out from a central point and you spin through an angle, a point on the rim of that circle of radius r will have gone through an arc length s. This is the general formula for the circumference of a circle. We've already discussed this. Or the speed with which a point on the rim of that circle is going around that circle depends on how big the circle is and how fast it's spinning. Or, if it's accelerating, the acceleration tangent to the circle will depend on how big the circle is and how much the spin is changing. Now, all of this depends on the fact that we have a circle of radius r where there is a central point that doesn't change. This only works when there is no slipping. If there is any slipping at all, this is broken. As soon as there's any slipping at all, these relationships right here are broken and they cannot be used to tie together translating and rotating. That would be sort of like we throw an object and it flies through the air, and then when it lands, it just slides. At that point, the motion in the x direction where it's sliding has been decoupled from the motion in the y direction when it's falling. And we haven't dealt with that in this class. We have not dealt with a situation where you throw something, goes through the air, and then when it lands, it slides. We are, however, going to deal with a situation where an object is rotating and translating, but the relationship is broken because it will be slipping. We're just not going to deal with that in this video. I do want to consider the effects of rolling on energy and how far something will go up an incline. So let's say that we have a bowling ball, and we're going to pretend that all bowling balls are solid spheres, and we've talked about rotational inertia in the past, so we're going to have to bring back rotational inertia. And it has a mass m and radius r, and it's going to roll on the floor with a center of mass speed of v. Now, what is the total kinetic energy going to be? The total kinetic energy is going to be the sum of its translational energy and its rotational energy. Adding those two together, splitting up the motion by the translating piece and the rotating piece, is going to allow us to find the total kinetic energy that it has. The translating piece is going to be 1/2 mv squared, and the rotating piece is going to be 1/2 I omega squared. Now, as long as it is rolling without slipping, and that's what we're dealing with in this video, there is going to be a relationship between the linear speed and the angular speed. That relationship, and I should write it this way, as shown on the previous board, omega is v over r. So we're going to be able to substitute and get rid of omega and put the spinning speed, the angular speed, in terms of the linear speed. Now, because I've also told you the bowling ball is a solid sphere, we can get rid of the rotational inertia and put that in terms of the known rotational inertia for the solid sphere, which is 2/5 mr squared. Making those substitutions will make it possible for us to add these two things together and find one overall total kinetic energy. So we are using, this is just like Ff equals mu Fn, or time. This is what ties together the angular and the linear so that we can find one overall expression for the motion. What you should notice is that the radius of that bowling ball does not matter. The radius of the bowling ball does not matter as long as it is rolling without slipping. As soon as slippage occurs, that radius is going to matter because there will be a torque from friction on that bowling ball. But right now, the radius is not going to matter as it rolls without slipping. It's going to cancel out. And we can cancel that 2 and that 2. So we will have 1/2 plus 1/5. 1/2 mv squared plus 1/5 mv squared. 1/2 is the same thing as 5/10. 1/5 is the same thing as 2/10. So this would be 7/10 mv squared. Notice that having an object that is not just translating, so this is the whole translating piece, 1/2 mv squared, and now we're also going to have it rotating. We have put more energy into this object. A rotating, or an object that is rolling, meaning translating and rotating together, has more energy at its disposal than an object that is simply translating. And you will see this in lab when I give you a variety of objects to roll down a hill, and then you compare that to an air puck that simply slides down the same hill. The objects at the bottom of the hill, they won't be moving quite as fast, but they will have more energy wrapped up in them. So we can, in part B here, derive an expression for that bowling ball, and having that bowling ball roll up a hill, that bowling ball is going to roll up to a higher height on the hill than if we had an air puck slide up the hill because of this extra piece of energy that is hidden inside the rotation. So we're going to take this kinetic energy and we're going to translate it into potential energy. So down here we have translational and rotational. And then up here we only have potential energy. The total energy at the beginning is going to be the same as the total energy at the end. And at the beginning, we had translational and rotational. And at the end, we have only energy due to position. The entire point of how far up the hill does it roll is that it is no longer translating and it is no longer rotating because those two guys will be tied together the entire time. There will be no slippage the entire way up the hill. On the left here, we already found that. That was part A. And we ended up with 7/10 mv squared. And then that height, we have a triangle here, it's going to be traveling up through mgh, but that h is going to be in terms of the length of the ramp, mg, let's call that d sine theta. A ramp of length d at angle theta. That d sine theta is going to be the height to which it rolls. So that distance, and I realize I'm changing the instruction from what is the height, to how far up the ramp. So now I'm going to solve it for d here. Notice, as with all other conservation of energy problems in which you have an object moving only under the influence of gravity, the mass doesn't matter. The mass cancels out. So the distance that it rolls up through is going to be 7v squared over 10g sine theta. Now, what if we change the shape of the object? And I'm not just going to change the shape of the object. I'm going to run this in reverse. What if instead of starting out with a rolling object on a floor that then rolls up a hill, what if we start out by having it start on the hill and roll down the hill? How fast is it going to be going at the bottom of the hill? We're going to go through this same process, except I've changed the shape and I've rearranged it to look for what is the velocity at the bottom of the hill. Theta d. Let's put a disk up there. And we're going to start that disk from rest. And then at the bottom of the hill, that disk is going to be rotating and it will be translating. But how fast will the center of mass be moving? Once again, we have total energy at the beginning, going to be total energy at the end. This time, the total energy at the beginning is potential, and at the end, it's going to be rotational. We are just simply running the previous problem in reverse. At the beginning, we have mg d sine theta, and then at the end, we will have 1/2 mv squared plus 1/2 I omega squared. It is important to start with the general forms of the energy and gradually get more specific as you go through to make sure that you are focusing on what is given to you in this problem, what you're using, what you're allowed to use, what do you actually know about the situation. Because at various points, you're going to find out that especially these two things get adjusted based on the specifics of what you were handed to work with. Now, in this case, I'm keeping it to the general simple case where we have a disk. Now, since we have a disk of mass m and radius r, I've shortened this to make sure that I have enough board space to write, but it's a mass m, it's a radius r. The ramp is length d. And also, rolling without slipping. Once again, we can use our tie between the linear and the rotational of v equals omega r so that we can get rid of the omega. And this time, what I wanted to know is what is the linear speed. Once in a while, you'll be asked what will be the angular speed at the bottom of the hill, at which point, instead of getting rid of omega, you'll be getting rid of v. All right, substituting. And notice the masses all cancel out. So we're going to have g d sine theta equals 1/2 v squared plus 1/2 of 1/2 r squared v squared over r squared. Once again, notice that because it is rolling without slipping, those r's are going to cancel, and it doesn't matter how big the disk is. So now we have 1/2 v squared plus 1/4 v squared. We've added 50% of the energy is going to be stuck in the rotation. Half of the translational energy, this is going to be 1/3 of the total energy, is going to be stuck in there. 50% of the translational energy gets turned into rotational energy. So the V is going to wind up being 4/3 because 1/2 is 2/4. 2/4 plus 1/4 is 3/4. We're going to have 4/3 g d sine theta. And don't forget the square root. Now, how does that compare to what if we just turned that disk on its side and let it slide down there and pretending that the ramp is ice so that there's no friction? What would that look like? Well, that would be all translational. All of the energy would be translational. None of it would be rotational. And then the speed would be, so this is v disk, v air puck, it would be moving faster translationally if it were an air puck. Notice that the 2 gets turned into a 4/3. The 2 gets reduced to 1.3333. So it will look like it's going slower, but that's because some of the energy is hidden inside the fact that it's rotating. And you will see this in lab when you roll a variety of different shapes down a hill.